Thank you. Appreciate you telling me that. I have that set up automatic on my other computer, but anyway. So in terms of geometry, I'll just go kind of quick, but since these two are parallel, this angle here would also be 50. And since that angle is 90, then this theta 1 is actually 140 degrees. So that's the angle I need to be using. And the same thing is true for the 70. For that reason, it'd be 90 and 70. So for this one, theta 2, that's going to be 190 and 70 or 160 degrees. And so now I have what I need. And so let's do what an engineer would do, or what I do when I teach my statics class. I say, okay, I need the sum. I can use the symbol with you guys. I need the sum of the forces in X to be equal to 0. So what does that look like? Well, I need the X component for the number 1. So since it's pulling left, I would say that would be negative cosine of some, so I'll just write this like force 1. I don't know what it is. So negative force 1 times the cosine of 140. Or maybe I don't even need the negative because the cosine of 140 will make it negative. Isn't that what I just did a minute ago? I took the force that I knew, 10 pounds, and then I multiplied by the cosine of the angle. So I'm doing the same thing here, right? So there's the X component, and then plus, if I call this one force 2, plus force 2 modified by the cosine of 160 degrees. And that's it, because the 400 doesn't do anything with X. I need those to add up to 0. That's it. What about the sum of the forces in Y? I need that to be 0 as well. So I have force 1 times the sine of 140 plus force 2 times the sine of 160 minus 400, because the 400 is entirely in Y. Notice I didn't have to multiply the 400. I didn't have to modify it with a sine or a cosine. Now you're welcome to. Isn't this angle over here 270 degrees? If you want to multiply that, if you want to multiply 400 times the cosine of 270 and 400 times the sine of 270, you can. You'll get 0 and negative 400 for those. I was just using logic for this. I need this to be 0 as well. So notice I have 2 equations, 2 unknowns. If I can solve those 2 equations, 2 unknowns, then I will have how much force is on each one of them. Let's see, I'm going to stick this in my graphing calculator, which I guess I can't show you. You linear algebra people probably have a sense of solving 2 equations, 2 unknowns. You've all done this before, so I'm not going to talk about it. I'm just going to get the answer to it. So I'm sticking it in my graphing calculator. I'm putting in cosine of 140. And the cosine of 160 and 0 and the sine of 140 and the sine of 160. In order for this system to work, you actually have to add 400 to the other side. So I have to put in positive 400 for that. And now I am solving that system of equations using technology. And if I haven't screwed up, good, I did not screw up. This produced force 1 as 1,099 approximately pounds. Force 2 came out negative. I'm going to round it off, 896. Remember I said what I drew wouldn't work? Basically, if it would have worked, I would have got 2 positive answers for this. But what that negative means is, oh, this arrow is actually not right. It's actually this way. Any of you have good, I don't know, mechanical spatial awareness? If you did pull down on this, can you see that force 1 is going to have to, as I drew right up here, kind of pull back to stop that? In other words, I had that one right. Whereas if you pull down, isn't force 2 actually getting shrunk? In other words, it's going to try to get shorter, if you will, and therefore this arrowhead is going to basically have to push back against that. So, you know, if I had some spatial awareness, I could have said, I already know which direction these are going to have to pull and push in order for this to work. But notice now it is possible. So force 2 is pushing down, and the 400 is pushing down, and then force 1 is pushing up, and they're actually balanced out to 0 now. And then the 400 makes no difference left and right, but force 1 is pushing left and force 2 is pushing right, and those balance each other out. And now that actually joint won't move. So an engineer uses vectors here to say, okay, cool. Now I know what size steel to buy. Does that make sense? Like you got to pick a cable that won't snap in half with 1,100 pounds on it. And by the way, in the real world, you wouldn't pick one that was 1,100 pounds. You'd, double it or go 1.5 times the size. But you see the power of what vectors do before we kind of slow down and kind of do the easy, like you can't make sense of this stuff any other way. That's what's so beautiful about it. So it's a force in a direction. That's really what it comes down to. So this is what you'd see a little bit of in physics, and this is what I teach in dynamics. And I'm teaching that right now. But let's just back off and look at kind of make sure you can get the questions right in the assignment now. So I mentioned already that kind of the notation side of this is a vector that was like -4, -4, 5, which could also be written as I equals -4 and J equals 5, in which case it's more writing. So that's kind of a worse way to write it if you're lazy. Why write letters and so forth? And then, putting it in order with 4 and 5, you kind of know which one is X and which one is Y. It sort of feels like an ordered pair. But here's the interesting thing. If you go to graph this, it's not right. Which one is it? What does the vector -4, 5 look like on a piece of graph paper? Well, the interesting thing is it's kind of like wind. In other words, it doesn't have a location. That's the thing that's really interesting. In other words, if I start here and I go left 1, 2, 3, 4, and I go up 1, 2, 3, 4, 5, then there's that vector. And sometimes, by the way, just for physics or something like that, if somebody called it V for vector, you might see a little arrow over the top of it, just kind of telling the person, hey, this is a vector. It's not an ordered pair. But the point is, it actually doesn't matter where you are. In other words, I could also be over here. I could be right here, and it would still be left 4, up 5. So these are both vector V. It's nowhere. It's not like you start at 0, 0. Does that make sense? Because this is out in the real world. There's no X, Y axis. You can put it any place you want. You saw me just do that in AutoCAD. I just drew it somewhere, right? I didn't draw it anywhere in particular. It's telling you how far to go from whatever point you're at. And so that works really good for something like wind, because you think of like, where is it? Well, it's kind of everywhere. So for that reason, you can make vectors from a couple of points. For instance, if I said, what's the vector from, say, notice it's an ordered pair, from 2, 3, 2, -5, 7. Notice there's a direction to this. Like if you get it backwards, then the arrow is going to be in the wrong location. So you can't just list 2 ordered pairs and say what the vector is. But again, that's just well, what is it? If I just graph this, notice I don't know where to put 2, 3. So I'll just go, I don't know, right there. So there's my XY axis. So I go to the point 2, 3. It's not a vector, it's just a point. And then I go -5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7. I go right there. Then there's my vector. So you know this from earlier math classes. Do you have to graph it and count it? Like I can count this now and say, look, X is 1, 2, 3, 4, 5, 6, 7. So X is -7 and Y is 1, 2, 3, 4. 1, 2, 3, I can count. Yes, I can. So there's the vector. But what do you do mathematically to those two ordered pairs to not have to do that? Isn't this just rise and run? Don't you just subtract? Y minus Y, 7 minus 3 is 4. -5 minus 2 is -7. Isn't that what we did for slope? That's just slope. So that's not hard. Just a second, I'm gonna. Oops, let me get something going here. My other computer is behaving worse and worse. Sorry, let's just take a second.
Did they make you upgrade to Windows 10?
The computer I usually use is just getting old and dying is the problem. I actually shut it off. I've shut it off right before class and restarted. It usually runs okay as long as it's gotten restarted. So no, I don't think it's that. So let's just do some, again, you can see from the applications that I showed you a little bit earlier, there's lots of kind of basic things that you can do that make this really simple. Let me ask you something about this. The other thing that will be asked is, if I call this vector V, you'll be asked for its magnitude, which is just code for length. Since you just saw a minute ago that the length of the vector, the actual length that you draw it, if it actually represents not literally a length, but like pounds. But if you draw it the right length to match the pounds of force or the miles per hour of the wind or whatever the measurement is, then the length of it actually means something. So magnitude just means length, and you already understand this. That's Pythagorean theorem. We just did that a second ago. So sometimes there's a symbol for this. Magnitude is, you showed the vector V. Sometimes you'll see one bar like this, but that's not so great because it looks like absolute value. Some books will have a double bar. That way it's not mistakable for an absolute value, but this is super easy. You just do Pythagorean theorem on those two things, and then you got the answer to that. So 49 and 16 is 65, right? So this would have a magnitude of the square root of 65, and so that's kind of cool that you can. But again, had I showed you this before these applications up here, I don't think you would have saw the power of that. Does that make sense? You wouldn't have understood. Because that's really what we got right here. We got the Pythagorean, we got the hypotenuse length of that force one is 1,099. We got that because of Pythagorean theorem. And the same thing happened in our previous example. We used the Pythagorean theorem to get that 14.84 kind of right back here. So
that looks like the notation for the determinant. That's not the determinant, right?
No, it's not determinant. We'll get to that. Let's see. Yeah, we're going to get to that with cross product. So determinant is, there's a determinant of a couple of vectors too that you can take. So again, I'll just do this really quickly because now it's sort of second nature, but I can add them. And you can see why now. So if I give you something like 2, 3, actually, let's do this a little more interesting. Let's call this vector V and this is vector W. You can actually even empower them. In other words, you could say, what is 2v plus W? And you could literally draw this, and I'll show you in just a second that you can do that. So 2v plus W. So you can actually multiply a vector by something, and what you're really doing is just doubling, you're doubling the length of it. I want you to see if you can picture that. I'll show you in just a second on a graph, but if I double that, 2v would just be doubling the two components. So everybody can get these questions right when they learn vectors, but not very many people get taught it in a way to realize how useful it actually is. So there I just doubled that, and then W didn't get doubled. And so now I can add them together. Notice something interesting happened. 4 plus -4 is 0, and then 6 and 5 is 11. So, but what does that look like if I drew a picture of what I just showed you? So mathematically, that's kind of embarrassingly simple. I'm getting the question right, but what actually just happened? Well, if I take the vector 2, 3, which is right there, notice again, I didn't know where to start, and I double it, another 2, 3. Does it make sense? That's 2 vector V's now. Again, head to tail. And now I'm going to go -4, 5. From there, I'm going to add to that -4, 5. 1, 2, 3, 4. 1, 2, 3. Let's see if I can move this without screwing it up. Three, 4, 5. And so do you agree that this is the result or the resultant? And notice that's 0, that's 0, 11. So there's a physical reality behind what you're mathematically doing here. When you're doubling something, you're literally doubling the length of vector V, and all you're really doing is just adding it to itself. That's what doubling something is, right? If you say I have $2 $6, that's really $6 plus $6. So all kinds of interesting questions that you can do around that. I could multiply, I can subtract. So you can add vectors, you can subtract vectors, all kinds of, I don't know, simple stuff that you can do there. You'll have a whole bunch of easy questions in this assignment that surround that concept. What I'm going to do now quickly is pull up, this is what I was doing a second ago, is I'm going to pull up my open math and just look at some other questions that are in there. Because most of the questions in your assignment do not have the practical component that I started this class with. It's just questions like I just showed you. You'll almost kind of feel like this is boring or dumb or a waste of time or something. And I'm just hoping that you see, it's actually more powerful than that if you don't make up boring questions like math books do. Let's see. So, in some of the questions, they'll just, do something like this. They'll just draw. I'm not even going to answer this. It's such a waste of time. They'll just give you a graph of that and say, how do you name that vector? And it's like, if you can count X's and Y's, then you can name that vector, like the whole first bunch of questions. Here's a question that, again, you already know this, but what if you were told a vector, we already did this too, but a vector was at 195 degrees and it had a magnitude of, let's see how your book says this. Magnitude of 24, let's say miles per hour. Like, could you put that in vector form? So that's the magnitude and angle, so the size and direction, but can you convert it to X and Y? Well, we did that earlier. If you take 24 times the cosine of 195 and 24 times the sine of 195. I'm going to write out one thing here though. 24 cosine of 195. If I write that out, I get -23.2. Again, you might see this in your assignment as being called I, or the X component. And the same is true. I said this already, but just have it written down someplace. If I do the same thing with the sign, I'll call that J. I also get something negative. The largest thing I would be concerned about this though, is that you'd go, yeah, that makes sense. For you to say, hey, 195 is over in the third quadrant. In the third quadrant, both X and Y are negative. Oh, look, both X and Y for me are negative. Of course, that's the case. And then you should also be able to visualize that because 195 isn't very far past 180 degrees, that this X coordinate would be much larger. Like that's almost 24. And the other one is way smaller. I hope that makes sense to you visually. But my point is, draw pictures of all this stuff. Like this is not hard. You already know. I haven't taught you one thing today that you didn't already know from polar coordinates. So don't make this difficult. They use the term I'm just looking at your assignment, force net, the net force. In other words, that's what you get when you add three forces together. I said the word result earlier. That's what engineers call it, but I'm seeing your assignment calls it the force net. That's fine. So we found, our very first question, we had three forces going different directions. We found the force net. We found the result of those by adding all their X and Y components together. In our first problem, though, we had to convert them to their XY components ourselves, but you'll have boring book questions that'll look like that green one there, except for it'll already be like that. They'll just say, what's the force net of this? And you just add them all up and they won't even be decimals. So super simple. But all I'm saying is don't just add these together and write the answer down and move on. Like draw a picture of it real quick so you kind of understand what this is accomplishing, or what it can do. And I won't write an example like this, but you should be able to go the other direction. Like here, I gave you the angle and the magnitude, but if I gave you the vector form, I'll write this down, but not solve it. If I told you the vector is -5, -2 in that form, and then I asked for theta and the magnitude, you should be able to go the other direction. But remember, when you go inverse tangent to find the angle, you got to be a little careful. You should be able to see that -5, -2 puts the vector pointing into the third quadrant. And that's one of the places that tangent's not going to take you. So if you just go inverse tangent, you're going to get it wrong for this question. So think about that. Just trying to see if there's anything we haven't talked about. Oh, unit vectors. So we haven't talked about unit vectors. I'm glad I looked. This is something I also did not understand very well earlier on. And so unit vector, what's a unit vector? What the heck is a unit vector? So to keep it simple, let's say you have this vector that is, I think I'll make this come out nice. So you have the unit vector 5, 12. It's not a unit vector yet. We're going to make a unit vector out of it. And so you say, okay, great. What's 5, 12 look like? It looks like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Looks like that. So the point is, notice that's long, like that's pretty long. And you can find the length of that by Pythagorean theorem. So by the Pythagorean theorem, this thing is equal to 13. I made this come out a whole number, the square root of 169, which is actually a whole number. So I don't have to have a square root. That's kind of cool. So by the Pythagorean theorem, that length is 13. Well, notice that's pretty long. And so why the unit vector is really important is, what if I want to like go in that direction, but what if that's the direction, but I want to apply like miles per hour to it. In other words, that's the direction the wind is blowing, and let's say it's blowing like 90 miles per hour. So we're saying this is like the wind, it's 90 miles per hour. And somebody effectively kind of measured it as being like over 5 and up 12. And so it's kind of going in that direction. Well, this is what a unit vector is for. So a unit vector is where you basically take the 5 and the 12 and you just divide each of them individually by the magnitude. There's the unit vector for 5, 12, done. Now, what does that accomplish? Like, why would somebody do this? This is the thing that it was never explained to me until I figured it out myself kind of down the road. Anybody know the answer to that from physics or anything else? Have you ever encountered somebody that said you'd seen unit vectors? Like, what's a unit vector for? Well, how do I get the wind involved? Does that make sense? In other words, really what I want to have happen here is because the wind is 90 miles per hour, I really want that length of that line to be 90. You see what I'm saying? I want that to be 90, not 13. And so this is how you get it. So the purpose of this in physics is because then this is what I would do. I would do what we just did earlier, which is I would take 90 and I would multiply it by 5 over 13 and 12 over 13. And that would create the actual correct vector then. And notice I didn't make that come out very nice this time, and that's okay, I'll leave it at that. And you know that multiplying a vector means you just multiply 90 by both terms individually. So if I take 90 times 5 divided by 13, I'm gonna get some decimal, 34.6. And if I take 90 times 12 divided by 13, I get 83.1. So this is the purpose. Now, if I did Pythagorean theorem on 34.6 and 83.1, what do you think I'm going to get? What's that going to produce? It's going to produce 90, like the length you actually wanted it to be. That's what a unit vector is for. Unit vectors are to give you a direction. I guess I'll say only. That's what they're really for. Again, your assignment's just going to say find a unit vector. You don't have to know why or what it's for. But this gives you a direction only. If you take 5 over 13, which would look like this, isn't 5 over 13 like about half? And 12 over 13 is right here. That's the vector we just made. We made that little tiny vector right there. Do you understand that since I did this, since this is 5 over 13 and this is 12 over 13, if you did Pythagorean theorem on 5 over 13 and 12 over 13, you end up with a magnitude equal to 1. Why it's called a unit vector is because you're making it length 1. That way, when I multiply by 90, I'm not screwing up my 90. You see the concept there? So now it allows me to take a direction and sort of get the correct length involved. That's the idea. So it's kind of direction only, since its magnitude is 1. Magnitude is always equal to 1, so therefore it's kind of a direction only vector. That's what's kind of cool about it. So I'm looking at your assignment. It says find the unit vector, and it just says, I mean, exactly what we just did. Man, this is okay. I think I figured because of the examples I gave right off the bat, we'd be kind of going long today, but it doesn't look like we're going to have to. It finishes with a really kind of a cool question that I'll illustrate a little bit, because I'm actually kind of curious to how good of a job they did getting this right. But somebody made up this sort of nerdy question, but it has to do with this. It's kind of like, let's go from here to here. So I'm going to travel to those 2 points. But the problem is, in this sort of playful question, there's like some obstacles in the way. Like there's a wall right here, and then there's a wall over here, and then there's a wall over here, something like that. And so you have to now plot a course to kind of get there. So as an example, and let's just try to do it with this. So I'll be a little more careful here and kind of draw this in a little more accurately. So could you plot course? Plot a course from A to B. And again, what this is another good illustration for how vectors work, because it's navigation. In other words, if you're in a plane, don't you plot a course? And ideally, you would just fly from an airport and go straight to the other place and you're done. But one of the things that often happens is, oh, there's a storm and I don't want to hit that storm. So I'll change course and I'll go, 40 degrees off course for, say, 100 miles. And then I'll plot a new course and then it'll get me back on track again. So, I was trying to go from here to here, but then there was a storm in the middle. So then you said, okay, well, let's plot a course up to this point, and then we can plot a course to that point. So do you see that as an application for vectors? It's a direction and a distance. In this case, it's not a direction and a force, it's a direction and a distance. So all kinds of just really powerful applications for this. So could you come over here and say, well, do you see that you have a lot of choices here? This is one of the things I'm really curious about on this question in my open math is, was somebody actually sharp enough to figure out all the answers to this? How in the world are they going to grade this? I found myself a little overwhelmed by that. So do you agree you have all kinds of choices here? Like I could go to any one of these points up here. Again, if I'm just trying to make my life simple, I don't have to go to, it doesn't even have to be right on a point, but I could go to any one of those points. I wonder if I could go to this point. Does that count as like hitting the fence? And that's not good. I actually don't know the answer to that in your assignment. But the point is if you can plot a course here and say, all right, I'm going to go to that point, and then I'm going to go to this point. Notice it doesn't hit the wall. I'm going to go to this point right here. And then I'm going to go, let's see. And you could pick a point that doesn't work, like this one, like, oh, I hit the fence. That isn't going to work. Kind of a duh. Seems easy to go just right there, right above the fence. So in this sense that I could then get there in sort of 4 vectors, if you will. Could it be done any faster than that? Is there any way to get there in less vectors than that? Doesn't look like it to me, but maybe I'm not thinking of something. The problem, by the way, has walls on it. You can't go just like out here and then straight over.
That was my idea.
Yeah, I suddenly realized, oh, that wasn't a very good question I just asked. So could you, and the cool thing about this though, and I think this is one of the things that makes an application of this really good, is if this was a navigation question, we were thinking of it as a storm or something a little more interesting than some robot in a maze, something of that nature. Does it make sense that you really don't, X and Y coordinates don't do you any good here? Do you understand that? Because you can't fly in X, Y coordinates and you don't even know what direction that is, but you do have the ability to know what angle you're heading, thanks to magnetic north, thanks to the Earth having a magnetic field to it. We have the ability to know that. So the fact that you can look at this right here and say that vector is 1, 2, 3, 4, 1, 2, 3, 4, it's 4, 4. The fact that I can say that vector is 4, 4, but that I would need to convert that to an angle and a distance, because that's what you can actually fly. Like I can keep track on a map of how many miles I fly. In other words, I need the magnitude and the angle for this. And fortunately, for the sake of the assignment, that's what it's asking for. So the fact that I can say for kind of this first course right here, I can say the square root of 4 squared plus 4 squared, the square root of 32, which maybe the assignment would say, give it to me perfect, square root of 32, or maybe it would ask for a decimal, who cares? Obviously in the real world, you wouldn't want to leave it that way because your direction finding capacity is going to be based on miles or something like that. And then of course I could say the tangent of theta equals 4 over 4. You shouldn't need to get out your calculator for this, right? What angle is that going to be right there if I go up 4 and over 4? So direction, magnitude. So there's the direction and magnitude for my first course, first point that I plotted. You do this second one. I'll count it for you since you don't have it sitting in front of you. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Notice you've got negative numbers in there. Quickly calc that magnitude and direction. So of course it's 5 negative 6, not 5 6. So you can't really screw up the 5 and the 6 with respect to magnitude. You should get 7.81. I chose to take the square root. So 7.81 miles I'm going to travel in, but what direction am I going to fly? Well, you got to be a little more careful here. Again, there's two choices. You could just look at this picture up here and just do this based on logic. You could say, hey, this is right triangles. So the tangent of theta would be 6/5, second tangent of 6 divided by 5. Notice I didn't put any negatives in that. I got 50.2 degrees, which literally means this angle is 50.2 degrees. But then you would have to be smart enough to say, oh, that's actually 50 degrees in the negative direction. You could add the 50 yourself. Does that make sense? That's just using logic, drawing the right triangle, looking at the picture. If you leave the negative in it, maybe it will take care of itself automatically. Maybe you don't have to worry about it. The answer is correct in this case. If you leave the negative 6 in it, if you say second tangent of negative 6/5, you get negative 50.2 degrees and it just takes care of itself. Remember my note sheet said you got to worry if you're in the second or the third quadrant. Notice we're in the fourth quadrant here. Weren't we aiming to the fourth quadrant? So the calculator gave us the correct answer. So I think you should be drawing pictures just to make sure you're kind of not screwing it up. So does it make sense armed with this? In the real world, you would have the capacity either in a boat or a plane where you're not sort of forced to follow roads. You'd be able to say, all right, set a course for 50.2 degrees. You might say toward the west or toward the north or something like that, rather than just, and my understanding is from different like military and commercial flights and so forth, that some people do this differently. Some people navigate from north and then they'll say from northwest and they'll turn toward the west 117 degrees. And then that's your bearing. That's how you give bearings. So you say north first, and you either turn right to the east or left to the west. And that's how they give them. Others will just give the entire angle, like 300 degrees. But again, it makes sense to measure that from north with respect to bearings. Does that make sense? Because that would be 0 on your compass is pointing toward north. And so it's like, what do you call north and how are you going to describe the angle? That can be a little different depending on what field you're in. But in our world, if you will, we call to the right 0 degrees. And so your angle has got to kind of consider that. So positive 50.2 wouldn't work here. Could you rename that as a positive angle? Yes, but notice in the bearing sense, you would never want to do that. In other words, I would not want to turn 310 degrees. I wouldn't want to turn the plane 310 degrees when I could just turn it 50, right? But of course, it'd be okay to say that. I don't know if your assignment cares. If it does, I'm sure it'll say convert it to a positive angle or something like that. But of course, that's easy. So I guess I'm interested that this is not hard, but you're going to need to have a good conceptual understanding of that, which I've given you a shot at having today. so that tomorrow when we go into 3D vectors, the first time you've ever graphed anything 3D, I think, or you've ever started considering that you live in a 3D world, there's not just an XY axis, there's also a Z axis. And we're going to start kind of playing around with that. I think just because I'm close to done here, I'm going to show you one thing really quickly. If you want to play around with it, share screen. I'll just do this live and see what happens because I don't have it on this computer. But if you go to, I need this on my computer anyway. If you go to a site called GeoGebra 3D. So your graphing calculator and Desmos are not powerful enough for this. So we need a new program. I'm going to favorite this if I can figure out how to get that off my screen. There we go. Let's see, is that favorite? Is that a favorite? Let's go to the favorites. GeoGebra. So this is really powerful. Notice I'm just holding my left mouse down now. And so if you decide you want to play around with this a little bit between now and tomorrow, it'll give you a little bit more conceptual understanding. I'll be using this with you tomorrow as well. But notice you can't tell what axis is what. There's 3 of them now, but what's what? It doesn't say that. You either have to memorize it. I remember, because I played around with this some time ago, there is, it's probably right here, settings. Show axis, show grid. There's a way to turn it on. If you see it, let me know, because I think I'm like really close right now. I think you can turn on the labels, show axis. Show axis positive. Notice it says positive direction only. Label X. There we go. I think this is it. Label Y. Label Z. I think that did it. Yeah. Turns out that's, if you want to just look at the colors, the red one is the x-axis in the arrow. Notice there's an arrow on one side and there's not on the other. So there's an arrowhead over here. That's positive x. This is positive y. So this is what you've done all your life right there. Everything you've done your whole life in math is that. You've looked at a flat surface. You've looked down from above at a flat surface. And by the way, there are all kinds of cool problems you can solve with just flat, like a bridge. You can look at it from the side view and you only need 2 axes. You only need in the real world, it'd be like an X and a Z axis because it's going up, but you could treat it as just an X and a Y axis and build a bridge in terms of engineering. But some shapes are more complicated than that, like an airplane wing or, like a bird flying in space. It's not flying in a 2-dimensional plane. And so it turns out the whole time the X was 0, or I'm sorry, the Z was 0. We had an X, Y, and a Z. It's just Z was 0 every time. But now you see, or now you're going to see that Z was coming towards you. And so the way you look at a 3-dimensional graph is like the XY axis is the ground, the flat surface, and you're looking down at it. And the Z axis is coming up. And I'll leave you with this. So if I go in and I graph the point 2, 3, 5, how come I can't see it?
Because your Z is stopping at 4.
Z is stopping at 4. Couldn't be said any better than that. So I can roll the mouse forwards and backwards. I'm rolling the mouse forwards and backwards. Notice if you can't spin this, you have no idea what you're looking at. You understand that? Because that A point right there could be flat on the XY axis down there and it has 0 for Z, but I can't tell unless I can spin it around. If I can spin it around and look at it from the side, oh, look, yeah, see how the Z coordinate is indeed 5. If I spin it this way, do you see how you can see the X and Y? But notice the arrowheads, you see I got it spun weird so that I got X going up and then Y going left. And so sometimes, it's like in order to have your brain not overload, you'll have to kind of spin it so X is level because that's the way you're used to seeing it. And then the arrowhead is pointing right, so that's positive. And so now you can see, oh yeah, look, X is 2 and Y is 3. And so I can actually see that this is true. But, again, I wonder about all the people historically that didn't have this ability. You just had to visualize this in your mind, right? You can't graph something 3D. You can break out graph paper and graph 2D, but you can't graph 3D. And so, wow, our power to graph equations in this dimension is really, really enhanced thanks to this free program. Unfortunately, it's not as good as Desmos in terms of being like the syntax of it is a little weird. I'm still actually figuring it out. We'll figure it out together. But some things are easy, like that point. Notice I never called it point A, and yet it made the label for me automatically. I just typed the point and it said this is going to be called A. So anyway, you might start playing around with that a little bit because we're going to make use of that as we go to 3D starting tomorrow. We're out. Stay after if you want to talk about your test. I emailed it back to you. Most of you, some people I put it into my open math, but you should have it back. So,
Thanks, Doug.
Pleasure hanging out with you guys.
Yeah, Doug, I emailed you back with some questions about the grading online. Don't know if you saw that.
I think I looked up when I was grading this morning, so I think I knew that came, but I haven't looked at it yet.
Gotcha. Yeah, I'm satisfied with my grade. It was just a little bit of confusion because I couldn't actually tell what I did wrong.
Well, can we answer that right now? Are you okay with having that?
I'm actually out of town right now, so I don't have access to my test or anything useful.
I do. I can pull it up. That's why I'm asking if you
Oh, yeah, that'd be awesome.
would be doing that publicly, and some people are
Oh, I don't care.
freak out. So. Incidentally, those of you that are left, this time when I graded your test, I actually pulled it up on my iPad and wrote on it, which my gut is that's nicer because I'm pointing at stuff and that's better for you. Do you agree with that? Or
Yeah, I like that a lot when you write on the paper.
Okay, I'll keep doing that. Vale, you got to help me find yours because I didn't rename them. Maybe your name's on it, but
Oh,
those look familiar.
yeah, it should be Calc 3, Chapter 12 test or something similar to that.
Hey, got it.
Oh, nice. So yeah, for 1C, find the time and the location where it lands on the freeway. I spent a lot of time using just a bad method that wasn't working. So I switched over to a note page because I ran out of room. And like quickly, I thought landed on the right thing of find where y equals 0 and then just solve for that. Use y equals 0 to find t, and then plug t in to find x, and then obviously y equals 0. So it's just.
I need to double check this because I think I graded this based on what I saw right here.
Yeah, that's why I
said
boxed the answer in notes.
And then I went down here and went, oh, good job. Because that's right. So I'm wondering if I should have came back and said, oh, he did answer this, which is what I'm doing right now.
That's what I was wondering what happened.
You did do that. So based on what I saw right here, I thought you were done. And you said, obviously, I interpreted it as, oh, obviously not correct. Like, you gave up, screwed up, whatever. But it's almost like I got down here and went, oh, he does get it. So did I take those 6 points off?
Yeah, you did.
Yeah, so let's fix that right now. That's exactly why I want you to bring these things up, because that's really dumb on my part. Is that the only one, or is there other issues?
One of the other ones, yeah, this one, I'm not entirely sure what I did wrong because you wrote tough there, but okay, so 2 cosine squared theta minus 1 is an identity that we like never use, but it equals cosine of 2 theta.
Mm-hmm.
So I don't know what I did wrong.
Yeah, so the fact that you converted it to that made it way tougher because now you got 2 different angles. You got 2 theta and theta, 2 different angles. It would have been better if you'd left this alone. In other words, if you go back here, I'm not sure what that is. It doesn't look like a 1. Oh, that's a bar. I see what you're doing. I got it now. If you left this alone right here, then you're home free. Because notice that's not that different than 2x squared plus x minus 1. In other words, if I replaced cosine with x,
Yeah, I actually tried using the quadratic equation and I thought it didn't work. I'd have to find my note page wherever it was for it. But yeah, it gave me just some weird decimal answers.
yeah, well, and part of it is because you might not have understood the graph you were looking at. And I saw from your graph, you sort of understood, you know, you sort of thought you had these two answers, if you will.
Yeah, because those are
problem
horizontal
is-
slope.
The problem is that this is how polar does this. In other words, that angle right there, that's the angle that you're after.
Oh,
And so that angle's like, you know, 45 degrees. And then, you know, whatever this distance right here, R is, like, you're going to get decimals for that angle and decimals for that length because they're weird. They're weird. It's not
right.
nice, kind of clean whole numbers. And so that was on the right track. If you solve that equation for cosine, I got my answer sheet. I won't belabor this point too much, but you end up with, from Pythagorean theorem, you end up with theta being equal to pi and equal to, I'll just give the decimal versions of them, 1.05 and 5.24. That's the angles you get from this quadratic formula of cosine.
Yeah, okay. I did actually get those and I discarded them because they didn't look right.
Oh, yeah.
Um,
And so,
interesting. I did not get the pi when I did it that way though. So do you have to do it both ways?
yeah, so you end up with, when you sort of factor this, you end up with the cosine of theta being equal to -1. That's what produces pi, because the only angle you're ever at where the x coordinate is -1 is at pi. So that
That makes
produces
sense.
pi answer. And then the other one is cosine of theta is 1/2, and you get two answers for that, which is 1.05 and 5.24. Those are happen to be exact answers as well, pi over 3 and 5 pi over 3. But basically, looking at this picture right here, that angle, that's the 1.05 angle right there. And then this one over here is -1.05 or the 5.24, where, you know,
Gotcha. And then pi, of course, is just all the way back around to the start, right?
no, it's actually not. I was going to say that's not obvious. Pi is actually this red point right here.
Yeah.
Because you're
Okay.
actually turning to here,
Mhm.
but then you're actually going a distance of 0. And so that point is actually at the point 0, 0. If you consider it as XY coordinates, it's at the point 0, 0. But you actually had to turn all the way to here and then go a distance of 0 in this direction, which actually puts you there. So the confusion is like trying to kind of exist in the rectangular versus polar world, like your smoke comes out of your head sometimes. So it turns out if you look really close, this comes in like this and sort of flattens out and then it takes off again. So it really does have a slope of 0 right there.
Gotcha. Thanks for going over that. Yeah, this test, I don't know what it was, but I felt like if you, however much time you gave me, I could have used. Like I was moving so slow through it.
Mm-hmm. Yeah, I know exactly what you mean. Yeah, and you had this one right. You just made one screw up someplace in your algebra.
Yeah, it took me like 10 minutes after reading your note of wrong sign to find where I made the mistake. And it was just, wow.
Was it done?
Yeah, when I added a variable across the equal sign, I kept its sign for some reason.
Mm-hmm. Right.
Oh, if you add -y, of course it stays -y. That's how that works. No, it's not.
And you, again, time's always an issue, but if you had graphed this with that negative sign in it, it wouldn't have looked like this.
Yeah, that's why I left my comment, because it actually made the right graph, just like mirrored over the x-axis.
That's right. I did read that.
Mhm.
Mm-hmm.
All right, thanks, Doug.
Yeah, good job. I'll fix your test grade. Thanks for pointing that out. I'm sorry about my mistake.
Oh, it's all good. I probably should have tried to be more clear that the answer was on a different page.
No, you didn't do anything wrong. It was there. It's all me.
See you,
Keep
Doug.
going. See you later, Bill. 87.99. What the heck is that?
Hey Doug, I just wanted to confirm with you, on our syllabus, it says that we have a chapter 13-14 test on June 17th. Final. So is the chapter 13-14 test going to be sooner?
Syllabi says. Sounds as though I didn't speak English. Oh, no, I don't think we're having a final. Isn't that good news? I thought we were, but I guess we're not. No final.
Yay.
Yeah, that's kind of nice. All right, thanks so much, Doug.
Thank you.
I feel like we've been doing unit vectors in 261 for a long time, but I didn't get a real applicable use for it. All I knew is I could multiply it by a scalar to get any directional vector I wanted. So that was really cool, seeing all the uses of my two worlds colliding, my two math worlds.
Yeah. I actually wish I could teach 261 because it's been so long since I took it that I don't. Kind of similar to what you were just saying, Martin. Literally the last time I took that class or had any interaction with that was when I was exactly your age, and I understood only, enough to kind of pass the class, not enough to deeply understand it. So the fact that these two worlds exist together doesn't click with me very well. So I'd really love to get into that material and see that a little bit. But yeah, it's kind of funny because especially what I noticed when I took that class was kind of what I showed you today, where it's like, hey, the math that we just did in 2 dimensions also works in 3. And then we sort of, we hung out at that thought for like 15 seconds. And then we went into 4, 5, 6, 7, 8, 9, a million dimensions. And then, now it was vector spaces. And so, I found myself just saying, well, I guess I can, kind of like you just described, it's like, oh, I guess I can multiply and, get an answer here, but I don't have any idea what it is. And because if you don't hang out in 3 dimensions for a while so that you can visualize what you're doing, because you can handle 3 dimensions, then, it's sort of lost. And so it's one of the cool things I'm going to be showing you that here, this next section is just how to get all this to jump to 3 dimensions and still work, in which case then you can be allowed to say, I see the pattern enough that I could do this in 4, 5, 6, and the math isn't any different. It's just that now you're creating things that, in a sense, don't as easily exist, or perhaps they do exist, but in dimensions that we aren't able to sense and see and so forth. So
Yeah, the math and the number crunching isn't too hard, but I think it was Raymond who shared the 3 brown, 1 blue guy. And after watching all his series, it's like what you did, but then you took it a step further. It's just like watching all the transformations go on a 3D plane. It makes me appreciate the number crunching a lot more.
Yeah, you realize, wow, it's amazing that works. Like you can just crunch the numbers and get it to work. Dot product and cross product are a couple of my favorites, because it really wasn't until I started teaching engineering that I understood finally what a cross product actually does. And nobody ever tells you this stuff. It makes me mad, but most of the things you learn in math are what I call kind of mnemonic devices. They're like a time-saving device. It's kind of like saying, I was thinking the other day, it's kind of like, I'm pounding a nail in, for instance. And so the question is, should I just keep grabbing rocks until they break and grab another rock and grab another rock? Or is it worth my time to stop doing what I'm trying to do here, which is hammer nails, and go build a hammer, make a nail pounder? And so now I'm, spending 3 days making this tool, and now I got this tool, and then I come back to my problem, and now I can just pound nails, man. I can just pound. So what happens in a math class is you're not building that tool very much. Somebody just kind of hands you one, and so you don't you don't have much of an appreciation for kind of how it works. And so dot product and cross product are like that. They're tools that accomplish something. But the funny thing is that even teachers don't actually understand what that tool is accomplishing. They can take a dot product and a cross product and get the right answer, but they don't understand. I mean, honestly, unless you've taken both math and engineering or both math and physics people understand the application, but not the math sometimes. And then math people are the opposite. And so you tend to not really get much of a sense of what those things are doing. So I'm excited to show you that stuff. Actually, please chime in with respect to 261, either preferably during class, just so that other people can, weigh on it too. And I might not immediately know an answer, but both questions you have in terms of those two worlds, but also even just observations that you make. Wow, we're learning that in 261 and this is what we're doing with it. Like, say that kind of stuff, because then it's kind of good for people to hear. Certainly good for me to hear.
I got you. I'll try to chime in with some comments and questions tomorrow.
Yeah, it's neat stuff.
Sorry for the little late test. It was like a minute late when I saw it, and then I was like, this sucks. I hope he gets the email.
No, I got it. No problem at all. Yours is one of the ones I didn't get to because it wasn't in my open math. I'll get that graded right now. So no worries at all.
Alrighty. Thank you, Doug.
Thank you.
I just had a question about, well, I guess a couple things on the test, but my main one is just about the graph for that first question with the golf ball.
Yeah, let's look at that. Throw Vale's grade in here real quick so I don't forget. Your test has your name on it, so yours is easy to find. Yeah, tell me about that negative thing. What's going on there?
So, yeah, when I graph it on Desmos, can I share my screen?
Yeah.
Yeah, once you stop. Okay. It looks like this. This is what I first typed in for my X and then Y. And it's like this when I thought that it should be like that.
You're in radians, I bet you.
Uh-oh. Yeah, that's what it was. Okay.
That explains it. I actually had a feeling. I had a feeling that was it when I was looking at it because, yeah. So you basically were just looking at it thinking. So you played around with it and said, "Hey, if I throw a negative in here, then it'll go the right direction."
Yeah.
So that made it look reasonably correct, but unfortunately, 34 radians is not 34 degrees. And so the answer it gave you down there where it hit is not, and that's why you were saying 255.
Yeah, that explains the second question that I had.
Yeah, I said on there. I almost wrote on there, were you in radian mode? But I thought you'll probably stay after and we could discuss it.
Okay, and on number 4, I was kind of confused about what you were asking about with the 2 other polar representations. And I thought that just.
In other words, this is the answer right here. Like that's the point graph. You turn 7 pi over 6 radians and you go at a distance of 8. Mission accomplished. There's your point. And I'm just saying, rename that name. There's other names you can give the same point. That's very unique to polar coordinates. The fact that you can name it other ways. So you were adding pi to it, which doesn't work because you're only adding a half a lap. You can add 2 pi to it. In other words, it's kind of like saying, hey, I turned 10 degrees. Well, that's the same as 370 degrees, right? Because that's a full lap around. So you're more than welcome to add full laps to it. So you could take 7 pi over 6 and add a full lap to it, which is 2 pi, not pi. And that would land you at the same location. That's why, and I think you got this you got 19 pi over 6 correct, but I think you got sort of lucky to do that because you added pi twice, if you will.
Yeah.
But the point is there's only one point here, and it's the one I circled in green. That's the right answer to this question.
Okay, yeah, I initially did think that I was supposed to add 2 pi, but then I guess I got confused and thought it would be pointless to add 2 pi because I ended up in the same spot, but that's actually what you wanted
Yeah.
in this case.
Yeah, another name for the same point. That's exactly right. That's all I meant. And it's also cool, just to make sure you understood this going out the door, that you could actually go here to this point. You can go to that point, which is pi over 6. But then instead of going in this direction 8, you can go in that direction 8, which is -8. So you can actually say the name of this point over here is turn pi over 6 for the angle, but then go a distance of -8. And that actually lands you at the same exact spot. That's very unique to polar coordinates, the fact that you can go backwards, if you will. So if you want to say +8, then you can just go any number of laps you want and land over there at 7 pi over 6, or you could go backwards. You could go this direction, which is -5 pi over 6. You could go -5 pi over 6. And then because you're at the right spot, you still just go a distance of +8. These are sort of the two classic answers to the question.
Okay.
But this one was okay, sort of by accident. Anyway, yeah, you probably just didn't understand the question. It's not like that math is hard.
Yeah, and number 6, I just messed up the substitution for the trig identity, right?
Yeah, that's it. You
Okay.
just got excited and saw 2 cosine squared, and you just lost the -1 that's in that identity, and that -1 just sort of killed everything that happened and kind of left you with questions like, you had those answers and you're like, oh, something's not right here. I don't get what's going on.
Yeah.
So
Okay.
yeah, in your case, I'm not really worried about that. The fact that everything else you did was great.
Okay. I'll see you tomorrow.
Okay, see you tomorrow.